Hello, everyone. We're going to start with the explanation of the Form 2 exercises included in the notebook I sent you. Okay, so let's begin. Well, first of all, I'll talk a bit about the dataset. The dataset is a classic one called HR Analytics, and basically you use it when trying to explain and show an example of predicting attrition in a company. Attrition is when employees leave, okay, either because they want to or because the company wanted to. Okay, so let's use this data in order to learn about feature engineering and evaluation metrics and methods. Okay, so first of all, we load the data set in here using pandas read CSV. Okay, and using this scribe, we can check what's included in every column. And for each column, we see the count, the mean, standard deviation, min, max, and 3 percentiles. Okay, so this is a sample of the data. What we will want to predict is the column left. Okay, but there's many other columns that we can use in order to learn or for the algorithm to learn about this left target. Okay, so the first thing I do is to make a copy of the initial data set that we have imported from the CSV so that we can work on it without changing the original conditions and original content. We can see that we have the target variable named left and 9 more features to work with. Out of this, this is wrong. As somebody pointed out in class, we only have two native categorical variables, which are sales and salary, while all the other ones are numeric. Okay, so let's start with an initial prediction that we will take as the baseline, and from that we will grow using feature engineering and complicating things a bit more. Okay, so we will be using logistic regression, and we will use 66% of our data as training data and 33% as testing. Okay, so first of all, let's create a function that will, or let's see the functions that will allow us to use this train test splitting. Okay, we import the function directly from scikit-learn. Okay, and first we need to define what are the features and what's the target. The features are usually defined as X, whereas the target is usually defined as Y. Okay, so now we will be using the function train test split. We will input the features and the target, and we will also input the test size that we want. We also define that we want our test data to be the 33% of the available data. Plus, I will set the random state as with a seed of 42, meaning that every or the splitting will happen randomly, but every time we reproduce it will be the same. So that this is for the sake of reproducibility. Okay. So let's train the baseline model. Okay. From linear model in scikit-learn, we will use logistic regression. Okay. These initial parameters, max iterations and penalty, are defined as 1,000 max iterations with no penalty. The penalty will come later when we will use lasso and ridge. Okay. So let's make the model train with our training features and our training target, Y train. Okay. So once we have run this cell, we see that we can check what are the columns with which we have trained our model. And by the way, we in the features that we will train our model with, I'm dropping sales and salary because they are categorical features. We can convert them using one-hot encoding, for example, which we will be using in the coming minutes. But for the baseline, I will leave them aside. Okay. So we check which features are we training with, what's the shape of this data set, and we can check the coefficients of our baseline model. Okay, if you remember from our first classes, we know that we will be creating predictions in the shape alpha x plus b. Okay, so since we have 7 features, our prediction will look like something like this: alpha 1 x1 times alpha 2 x2 times alpha 7 x7 plus beta. Okay, so all these alphas here are the values that we are finding when calling on the coef property of our model. Okay, so for each of these numbers, we can multiply that for our features, and then summing up the beta parameter, which can be found by calling the second one on this. Oh, of course, I didn't run the whole thing. So yeah, using the first component on the coef property, you can access the alphas, while calling on the second one, you can access the betas. Okay, let's run all this. Okay. I thought the coefficient. Let's check how to find the beta coefficient or the intercept in our linear model. Okay, so we can basically ask Google, because I don't remember. I think it's called intercept, but let's be sure of that. Exactly. It's called intercept. So our beta in this case, our beta here can be accessed using intercept. Okay, so in our case, beta is 0.2018. Okay, so knowing this, we can create a dictionary and using zip as well, so that we can map for each feature what's the parameter that the coefficient, the logistic regression has assigned to it, so that we can build a sort of feature importance according to the alpha value. Okay, the higher this value, the more impact on the final prediction. Okay, that's how we will create this idea of feature importance. Okay, I used this function called getFeatureImportance, which receives the classifier or the trained model, and also the name of the features in the same order as you have trained with. And by zipping these two, or by creating this dictionary, sorry, first one with the name variable and second one with the coefficient, with the name coefficient, we can create a data frame, okay, like this one in here, okay. And for each one, we will have its coefficient and the bar plot like indication of how big it is and how and whether or not it's negative. Okay. So now let's use our trained model to predict or to create predictions. Okay. For creating predictions, remember we will be using the X test data frame. This, as I already mentioned, this is X train, this is Y train, this is X test, and this is Y test. Okay, this being 33%, this being 66%. Okay, so this data frame here, this portion of the data is the one we are going to be using to create predictions. So let's do exactly that. Also, in order to evaluate how good these predictions are, we will create another function called evaluation metrics, in which I am using almost all of the evaluation metrics I explained in class: accuracy, precision, recall, F1, Cohen's kappa, and MCC, so that we have the full report on the performance of our predictions. Okay. Also, we can use the plot confusion matrix function included in scikit-learn in order to visualize the confusion matrix that we will be creating in our classification problem. Okay. Something that you guys have realized and we discussed during the forum 2 on Slack is that the order of which of the labels that you include in this parameter here, labels, will be assumed as the first one will be the negative value, the second one being the positive value. Okay, so in our case, it'll take this shape and will calculate precision and recall accordingly. Okay. So let's run our predictions, our evaluation metrics, confusion matrix, and let's check the evaluation metrics for our prediction. We have a 75% accuracy, but precision and recall are quite low. Okay, this means that our model is good at finding true negative and true positives. Okay, but it's not so good at catching all the positives and all the negatives, because we can see that it's clearly missing lots of positives and negatives as false positives and negatives. Okay, so what can we do to improve this? Well, the first idea is to use feature engineering. Okay, let's see what types of data we have included in our original data set. Remember that we had removed the categorical variables named sales and salary. So now let's include them and also use them in a way that the logistic regression algorithm know how to, because if you feed it with categorical features, it will not work. Okay. So first of all, let's factorize our features. As we saw, two of the categories are categorical. Plus, by analyzing the rest of the numerical features, we see some of them can be encoded as categorical and then re-encoded as with label encoding or one-hot encoding, so that we keep the sense of categoricalness of these features. Okay, these features are sales, salary, promotion last 5 years, left, which is our target, and work accident. So we will be using the as-type method in pandas to convert into another type. Okay, we will be converting all of them into categories, and once we have done that, we have 5 new types, which are work accident, left, promotion last 5 years, sales, and salary, now encoded as category. Okay, we can also do more stuff to our data. We can, for example, bucketize it so that we convert a numeric feature into a categorical feature by selecting different bucket sizes. And if a certain observation falls into a certain bucket, it will be assigned that class that we have artificially created. In our case, we did this bucketization for satisfaction level bin feature and last evaluation bin. Okay. By the way, let me rerun these cells. Okay, now we will perform the bucketizing, okay, by using cut, the native method cut included in pandas, okay. And now we can also for the features number project cat and time spent company cat, we can map a name to the bucket, okay. We can do that using the map function from pandas. It's really useful. Basically, map what does is you feed it with a dictionary-like structure, and for each bucket, it will be assigned a name. Okay. So we have already worked with converting numeric to categorical and bucketizing numerical, and by assigning a label to each bucket, converting them into categorical again. Now let's go for hunting NAs. This data set here, you were quite lucky. We were quite lucky with it because it didn't contain any NA, but this is not real life. In real life, you will find plenty of data with NA, and it's generally up to you whether or not to remove it, but it's usually to analyze if it's good to maybe input or infer the data that should be included in that NA as, for example, the median, the mean, the previous present value, the next present value. So there are plenty of ways to do this. So it's generally a good idea to spend some time on this when you find NAs. Okay. As I said, our data set does not contain any NA, so let's skip this step. Okay. And now let's dive into outlier analysis. Outliers analysis is, again, something you should always spend some time in when working in feature engineering, because it's not that you should remove always outliers, but you should remove outliers if the effect these outliers cause in the target or in the prediction are not important. Okay, because if we can use for, especially in models like logistic regression or linear regression, when the distribution of our data is expected to be normal. If we have plenty of outliers, meaning we have long fat tails, it's better to convert it into a more kind distribution for our data, but only if the effect is negligible. If the effect is not negligible, which usually happens as well, you should train with your outliers too. Okay. So let's visualize the outliers by creating a box plot with Seaborn in this case, sorry, with Matplotlib. And we can see that we have some outliers because by by default, when calling box plot, we will be using plus minus 1.5 times the interquartile range. And we can see that the interquartile range, or sorry, the Q75 plus 1 times 5 IQR falls around 5, so everything beyond 5 is considered an outlier. Okay. In this data set, when removing the outliers, we will be removing plenty of observations in our data, which is a huge chunk. So always be aware that removing all of the outliers might result in removing lots of information from other features. So this is just an example of how you can do it, but always analyze if it's worth doing it. Okay. This is the same box plot, but without outliers this time. Okay. And now what I did here is to check first which are our numerical features from which we want to remove the outliers. Okay. And for each one of these, using a for loop, I'm going to be using the remove outlier function that we just defined in here. Okay. Which basically removes every value outside this range that we have defined here, which is what you already know about IQR and the Q75 and Q25. So let's run these cells. As I mentioned already, we have removed quite a lot of observations because of this. So again, put some time into analyzing what's the effect of removing this versus not removing the outliers. Now we have removed the outliers, we have dealt with NAs, we have converted all of our categories into from numeric to categorical, those that were fit to do that. Let's do one hot encoding. Okay, if you remember from class, one hot encoding consists in converting a feature, a categorical feature. Okay, for example, this one I'm creating contains ones and zeros. into as many new features as different categories you have in the original one. Okay, well, this example with zeros and one is not super didactic. Let's use categories A and B. Okay, so we will create two new columns. The first one for observations that contain target A, target equal A, or feature equal A, which is this one, not this one, this one, not this one. And for the other one, the complementary. Okay, so we will be doing this for every categorical feature that we have created. Since we knew which variables were, which are the work accident left, promotion last 5 years, sales, salary, number project cat, and time spent company cat. These last two were the ones that we bucketized and used map to assign different categories. We will convert this array of features into ones and zero features, one per each new category that we have for each feature. Okay, we can use for this regard the sorry, let's yes, this is where you mentioned that I had sent you this data notebook without the initialization of the one-hot encoding. Okay, so if you see from the imported libraries, not here. Well, okay, I'll do it on the very cell that we are creating this time. Okay, we will initialize the, well, let's first import it. I think it's in scalar and preprocessing. Let me check. Yes, one-hot encoder. So we will initialize our one-hot encoder object using this function that we just found, which is, well, first let's import it. Preprocessing, import one hot encoder. And we will initialize it. Okay, and now by feeding to this initialized encoder the array of categorical features that we want to convert, and then we convert that into an array again, we will keep a matrix of zeros and ones, which will be, in our case, we are just keeping this array or matrix of zeros and ones, okay? Okay. I didn't. What did I do with this? Oh, okay. I think I've deleted somewhere. Okay. Wait, 1 second. Let me pause this. Let's see if I know how to. Oh. It looks like I don't know how to pause this. So let's create it from scratch. Okay, so we have this, okay, plus number project cat. Okay, okay, error. Hmm. Okay. Let's see what's the um, what's categorical calls first, and what's in HRDF. Okay. Well, excuse all this improvising because I think I forgot something about this. Now I feel you. You're struggling with my assignments or my forums. A ver, what the hell? This is the binning of our data. Then I did the mapping for each bucket to a certain level. Okay, it's included here. Now we have everything. Okay, let's jump into one hot encoding again. Okay. Okay, now it works. Okay, so well, basically, I had just forgotten to run some cells uh, upwards, so I just did that. And now we have our matrix with zeros and ones for each categorical feature that we had defined in this list of names. Okay, I don't know if you know this operator here, but what this plus equal operator in Python does is it takes for the previously variable named as categorical calls, it adds the following value. In my case, is a list, but you can do that as well with, for example, a normal variable name foo if this equals one, foo plus equal one will give us, well, sorry, two. Okay, we can also subtract, giving us zero, and I don't remember if you can multiply. Um, yes, you can, and I guess divide. Yes, okay. So we have our matrix of zeros and one for converting the categoricals into one hot encoding. let's get the new features that we have created. As you remember, those are the features that we have created in here, for example, XA and the XB, or in our case, for example, we had work accident. We had a column called work accident with zeros and ones. And now we have work accident 0 and work accident 1, and we will have zeros and 1 per each one of them. Okay? This is all the new categories that we are including in our dataset. So now let's put everything together in a data frame. First, we will be including all the zeros and ones that we have created with the names that we have defined with this get feature names method from one hot encoding. Okay, so if we do this with a data frame, we can see that this is all the new features that we have created. Okay. This is from the other day in class. And okay. So this is basically the whole pipeline that I've been doing in different parts. First of all, we defined the categorical columns. Then we removed left because we don't really want to one hot encode the target. We want it as it is. And then we define the numerical columns, which are the columns that are not categorical, by using this filter. Okay. So now we initialize the one hot encoder. We define the data frame that we want to include our new features in, and we will create it by using the fit transform method and by calling the get features name so that we know which is the name of each new feature that we have created. Okay, and once we have this one hot encoding data frame, we will concat that data frame to the previous one only for numerical columns. Okay, this is done here, and I am concatenating concatenating sideways. First of all, the numerical ones. Second, the one hot encoded ones, and third, as a single column, the target. Okay, and this is how it looks like, our final data set. Okay. Okay, we have plenty of new features and plenty of new types. Okay. So let's see how this data has changed from the beginning. If we call D types on the original data, we see that we had 2 categorical features while the rest were numeric. And if we do the same with the new data set that we have created, we see that we only have numeric features. We have plenty of one hot encoded features like work accident 1, promotion last year, sales, salary, number project cat, time spent company cat, and left. But if you remember left, we will keep it as category because we really want to see the classes that we are predicting. Okay. This is well, this was an example on how to check the histogram in order to create the different buckets. Okay, using in this case the function histplot from Seaborn. Okay, and this is the difference between the original feature as a continuous variable, and this is the one that we have used when binning it in 4 different buckets. Okay. So now that we have worked on this pre-processing and feature engineering, let's create the second predictions. Okay. Again, we will be using train test split for keeping 66% of our data as training data and 33% as test data. Okay. Let's run this. And now we will train a new logistic regression estimator. Okay. We are maintaining the max iter and penalty parameter so that it's comparable to the previous one. And now if we what's happened here? Get feature importance. I have it defined. Here, great. Okay. Okay, let's see the feature importance of our new data set after the feature engineering. Okay, we see that there are some features, for example, number project cat very high, which has a very high coefficient for our logistic regression approximation. And also number project cat low has a very high value, but on the negative side, okay? These two features will drive most of our prediction, okay? So now we can use the predict method on our test feature set in order to create predictions. And let's analyze our new predictions, okay? As you can see, we have found a considerable increase in accuracy, precision, and recall, okay, as well as F1, Cohen kappas, and MCC, meaning that our estimator or our data is really good to predict the left feature, okay, and if we compare with the original data, we see that it's almost a stupid version of this feature engineered one we have created, okay? As I mentioned, every metric has improved by performing feature engineering, and so this is good. And now let's perform some feature selection, okay? Because we have plenty of features that we created with the one-hot encoding, and we can use chi-squared or information gain to decide according to a certain metric whether or not a feature is to be included in our data or is relevant to our data, okay? So let's start first with, oh no, it's done at the same time, comparing the chi2 and information gain, okay? We can use the select k-best feature selection method, and for this method, we can specify which function we want to use in order to perform this selection. For the first one, chi2 selector, I'm going to be using the chi2 function. And for the IG selector, I will be using information gain, okay? So we fit our selector to our data, the whole data set, both training and test, because we really want to see the effect of this selection on all the data, not only on the training data. And then we get which indices in our data set are maximized or minimized by these functions using argsort. Basically, this function is a NumPy function that sorts your data according to a certain value or feature in it, okay? And then what I did is for each of the columns that we find in the features, we append that to the list created here called chi2 features and IG features, so that we see the sorted feature according to each one of the methods. Remember, the methods were chi2 and, well, information gain. And we can plot that, okay? So we can see that for chi2, satisfaction level bin is the highest feature, okay? So that is the one that contains let's say, the most relevant information according to chi2. Whereas for information gain, we also have satisfaction level and satisfaction level bin, which is a good thing, that the most explanatory feature is the same in both methods, okay? So now what we can do is, according to each one of the two methods that we have performed our selection, okay, we can compare the results using them or not, okay? So in this cell, what I am doing is first defining a classifier, which will be, again, logistic regression with 1,000 iterations and no penalty, no regularization. And for each feature and its value included in this, sorry, for each feature name and its sorted features, okay, what I'm gonna do is first uh, create subsets of train and test according to these ordered features that we created according to the different methods, train a classifier, predict according to the subset X test, okay, and then calculate the accuracy. So, well, let me go back because I need to run this. Okay, we have again the graphs that we explained a while ago, and now by using this cell here, we can compare the features and whether or not they are important to be included in our data. Okay, so we have created this comparison data frame. Okay, and oh, now it should work. Well, when it finishes, you can plot the evolution of the information according to how many features you include. Okay, for both methods, Kai2 and information gain, and we saw that the sweet spot, the highest value was achieved around 5, 6, 7 features included, okay, for the 5 top features for each one of the methods. So we can continue using that and specify it, okay, when training, and we can go ahead by using this filtering. What I'm doing here is filtering our train and test data according to the two methods, Kai2 and IG, and what I'm keeping is the top 2 features in each case, okay, both in train and test. So now we have created the subsets. Now we can train the classifiers, maintaining the parameters that we had in the beginning, okay. We fit and we predict. We fit and we predict for both methods. Okay, and now we see that performing some feature selection according to Kai2 and information gain improve the more or less the accuracy, not so much the precision in the case of information gain, but overall there is an improvement when you perform some feature selection. Okay, this is something to be tested and iterated when you're working on machine learning, because not always it's useful, but definitely it will always help humans to understand better the data, and it will simplify your model. Remember that not always more complexity equals a better performance. Okay. So now let's go to the final part where we will be using feature selection method, an embedded method using rich and lasso regularization. Okay. As a rule of thumb, think of regularization as not letting the model learn that much about the training data by using certain like interruptions or interruptions or methods to avoid the model to learn too much about the training data. Okay. With the original classifier, we would be, for example, with linear regression, we would be using the residual sum squared, which looks like this, okay? But with Rich and Lasso, what we are doing is adding an extra regularization term. In the case of Rich, we will be adding a term which is proportional to the square of the parameters. This beta here are the parameters that we were with which we were multiplying the data. Okay, here, here, here. Okay, so we can train a model that performs ridge regularization within the training step or within the training step by indicating what type of penalty are we using. Remember that in the past we had been selecting none as penalty, but now we will be using the L2 penalty term for performing ridge. Okay, and as you can see here, when doing this, when it runs, okay, we see the new coefficients that have been assigned to each feature in order to create the predictions. Okay, we can now predict and evaluate using ridge methods. Okay, and we see that it's more or less as with feature engineering, maybe slightly better. Okay, so there's an improvement with just using feature engineered data, but still the best option is to use the Kai2 selection for the features. Okay, almost every metric is better when using the Kai2 feature selection. Okay. And we can repeat that with Lasso, which is the L1 regularization. The cool thing about Lasso is it can be used as feature selection method because Lasso not only reduces the size of these parameters, but also for some of them will be removed completely. Okay, and according to this formula here, this is the term that we will be adding to the RSS originally. And this one is proportional to the absolute value of the beta parameter or the alpha in our case. So we can again train our model with Lasso regularization. Remember that we have to change the penalty in order to apply Lasso, and also for using Lasso, we also have to change the solver that lies within the estimator itself in order to be able to perform Lasso. So again, we have all these new parameters. You see now that we have converted some of them to 0. Some of them will have no weight in our prediction, like average monthly hours, salary highs, sales management, work accident want, etc. Okay. Now let's evaluate how good is our Lasso regularization when predicting the target. And we see that it's a bit better in accuracy than ridge, okay, and almost in every parameter, but still Kai2 is the best method according to the ones we have tried today for predicting this left variable, okay. And yeah, that's it. Hope it works for you and it helps you understand better what we did. And I will share with you this very notebook now so that you have the running version. Okay. Well, thank you very much and see you next time.